This isn't what I thought it was. Where is it? I guess this is it. Okay. Yeah. I think maybe I worked backwards. I'm not sure. Actually, let's just start here. Okay. Next thing we wanted to do was make tables and graph the function y equals x squared plus x cubed. Okay, well, pretty easy. We can make a table for x squared. We can make a table for x cubed using the usual x values. Now, I didn't originally include -1/2 here because we can always use symmetry and figure out what happens to the value at 1/2. And then I realized it was going to be a good idea if I did this, since I want to add these values. So the -1/2 is in yellow here, kind of inserted between the -1 and the 0. We know these numbers, we know these numbers, we know these numbers. And these numbers just follow from these numbers. X squared plus x cubed. For x equals -2, that's 4 and -8, which is -4. For x equals -1, that's 1 and -1, which is 0. For x equals 0, it's 0 and 0, which is 0. Well, that's a no-brainer almost. For x equals -1/2, it would be 1/4 and -1/8, which is 1/8, positive 1/8. At 1/2, add 1/4 to 1/8, you get 3/8. And then at 1 and 2, you get the values that you see here. Those are easy to calculate. Okay, so what we want to do is graph this function. So, and when we graph it, when I originally graphed it, I didn't have these yellow numbers in here. So what I got was a graph that looked like this. So we asked the question, well, how do we make a graph through these points? There's another point way up here, I didn't include that. How do we make a graph that goes through these points? A smooth curve that goes through these points. Well, one thing we definitely don't do is we don't go in a straight line from here to here and then a straight line from here to here, do we? We can't do that because that's not smooth. There are corners. There's a corner right here. Okay? There might not be a corner here. There actually wouldn't be, but there's definitely a corner here, so we don't do this. We also don't do this. We don't curve it up to here and then all of a sudden just go straight across and then up. We could curve it a little bit more as we approach this point so that the graph becomes horizontal at this point and then moves across in a straight line and then curves upward here. That would be smooth. Okay, there are no corners, no jagged, sudden changes in direction. The change in direction just proceeds very continuously and smoothly. We don't do any of those things though. What we do is we go ahead and maybe evaluate this at -1/2 and find that, okay, this doesn't work, and this doesn't work. And then we find a piece of yellow chalk, and I might or might not be able to do that in a reasonable time. Yeah, don't see any. So I'll use the closest thing to yellow, which is green. Cross this out, cross this out, cross this out. None of them have this point. None of them correspond to this point. If we include this point, then the graph will come up here, come down here, and then come up around here. Now, we're not guaranteed that the graph doesn't maybe come down through the axis before going back up here, but there's a way to guarantee it, and we'll see that when we talk about the zeros of a polynomial function. Okay, well, x squared, x cubed, x to the 5th, etc. are, well, okay, let's do it in the order I did it. This is what we call a polynomial function. A polynomial function I'm going to define, and if this is consistent with any other definition you'll see, any other valid definition you'll see, is a sum of multiples of power functions for non-negative integer powers. Power functions with non-negative integer powers. Okay? Now, that's a great definition, it's a valid definition, and I don't think it can be challenged. It could be made a little more specific, you know, multiples by what and stuff like that, but we don't worry about that, we know it's gonna be numbers, real numbers. Okay? But what in the world do we mean by power functions? I've never defined a power function, I've alluded to them, I've given you examples, said these are power functions, but what is for sure a power function? So this is a great definition as long as we have a definition for power functions. So let's define power functions. Well, it's very easy to define power functions. Power functions, a function of the form y equals x raised to the p, where p is a real number. Okay? Now we've already seen x to the second, x to the third, we just looked at x to the fourth and x to the fifth and thought about what happens if we go to x to the sixth, seventh, eighth, ninth, even and odd powers and all that stuff. Those are all power functions. Okay? So for example, x to the fifth is a power function. All we have to do to show it's a power function is to show it's of this form, and it's certainly of a form x to something, and that something has to be a real number. Well, x to the fifth is of this form, y equals x to the p, with p equal 5, and 5 is a real number, so it's a power function. What about 1 over x squared? Is that a power function? Well, some people say, yeah, it's x squared. Well, it's not x squared, it's 1 over x squared. It's still a power function, but the power is not 2. It's not an x to the second power. It's a 1 over x to the second power, not a power function in this form, but it is a power function, okay? It's not an x equals, it's not a p equals 2 power function, but it is a power function because 1 over x squared is x to the negative 2. X to the negative 2 is the same as 1 over x squared. So this is a power function, but with p equal to negative 2, not to p equal 2, okay? And notice that, you know, this is a negative integer, isn't it? Negative 2 is a negative integer, and our power functions that make up polynomials have to include only non-negative integer powers. So we would never include 1 over x squared as part of a polynomial, okay? The power has to be non-negative, and it has to be an integer, meaning no fractional part. Not negative, there's no fractional part. Okay, square root of x. Well, I hope know that the square root of x is x to the 1/2 power. Why is that? Well, if you multiply the square root of x by the square root of x, you get x. And if you multiply x to the 1/2 by x to the 1/2, you get x to the 1/2 plus 1/2, which is x to the 1, which is x. So this squares that to give you x, the square of this is x, so these are identical. Now that's a power function, of course, then, with p equal to 1/2. X to the pi is a power function with p equal to pi. Now, lots of luck trying to evaluate that one. Just, you know, plug it into your calculator, it'll work fine. Most of us will never know how to actually evaluate that other than by punching it into the calculator, and for 99.9% of the population, that's all you need to know. So we're not going to worry about that. You're doing the Taylor expansion, and then other approximation methods. Okay, well, still have not approximate pi, though. Okay. Among these, the only non-negative integer power is 5. 5 is a non-negative integer, 2 is not a non-negative integer, 1/2 is not an integer, it's a fractional part. And pi is certainly not an integer, okay? So, when we define polynomials, well, this is a polynomial because x squared is a power function for p equal to 2, and 2 is a non-negative integer. And x to the 3, it's a sum of these, okay? X to the 3, 3 is a non-negative integer, so this sum forms a polynomial. All right, well, I'm going to give you a little preview of something's coming up, but I'll end this first.